section 4.1 is going to be on exponential functions. So, first thing we're going to cover on exponential functions is the definition, which is this. An exponential function with base b is defined by the function f of x equals b raised to the power of x, or f of x we know is the same as y equals to b raised to the power of x. Now, that base b is just a number. Okay, so basically an exponential function is whenever we have a number raised to the power of x, in which something you need to keep in mind is that that number b must be a positive number, other than 1, of course, because if it is not important if the b is 1, because 1 raised to any power is always going to be 1. So what we are interested in is any base that is greater than 0, but of course not 1. Any number as long as it's greater than 0. Now, let's go ahead and start graphing a couple of these functions. And the first thing we're going to do is this. Graph the given function f of x equals 5 raised to the power of x by creating a table of coordinates. So I am going to be using the same idea that I used to tell you before. I'm going to create the table by using the values -2, -1, 0, 1, and 2 as before. So we're going to have x and f of x, which is 5 raised to the x power. Now for the x's, we're going to use -2, -1, 0, +1, and +2. Now keep in mind the following. This is something we did in section P.3. If I raise any number to a negative power, that represents the reciprocal of the number. The reciprocal of 5 is going to be 1 over 5, and that makes the exponent a positive exponent. So that's the same as 1 over 5 to the second power, which is 1/25. That's what that point is going to give us. The next one, 5 raised to the -1 power. Since it's a negative exponent, that also creates a reciprocal, which is 1/5 to the +1 power, which is just 1 over 5. The next one, anything raised to the 0 power. This is another definition we cover in section P.3. Anything raised to the 0 power equals 1. 5 raised to the first power equals 5, and the last one is 5 raised to the second power is 25. So this is going to be our table, -2, and then 1/25. If you want to know basically an estimate for that, you know that 1/25 is a number very relatively close to 0. So 1/25 will be 0.04. Basically, that's an estimate. The next one is -1, and 1/5 is 0.2. The next one is 0, 1. The next one is 1, 5. And the next one is 2, 25. So let's graph those points on the grid right here. So -2, and keep in mind that this number 0.04, it is almost 0. So it's going to be very close to what we call the the x-axis. So -2, 0.04. So it would be almost touching the x-axis. The next one, -1.2. So 0.2 is a little bit higher, so somewhere around this area. Then 0, 1. 0, 1 is here. Then you got 1, 5. And the last one is 2, 25, which is all the way up. So if I connect these points, this is what the graph basically is going to show us. And then after this, it's just going to disappear. Okay? So an exponential function, it is defined, or it is basically, one of its properties is that it is special because of its, what we call exponential growth, which is its rapid growth. Okay? So we see that once we hit the positive x values, it grows rapidly. It increases rapidly. So what happens now as the graph keeps on going to the left side? Now, if we decrease the value of x, for example, what happens when x is -3? What happens when x is -4? What happens when x is -5? So, as you can see, as we decrease the value of x, right here, as we decrease it, what is happening to the value of y? The value of y, it is also decreasing. But is it decreasing means that it is getting to a negative value? No. What's happening to the value of y is that the fraction is getting smaller and smaller, and basically it is approaching what we say, it is approaching the number 0. Right? So if we keep decreasing the value of x on the left side, this graph is going to keep approaching and approaching and approaching and approaching 0, but it will never get to 0. So that's what this graph has as one of its specialties. So it would have what we call something from section 3.5, as you remember, a horizontal asymptote on the line y equals to 0. What does it mean by horizontal asymptote? It means that the graph will get very close to, but it will never get to 0. That's what's going to happen as the fraction gets smaller and smaller and smaller. Okay? Now, let's work on another graph right here. So we're going to continue with this function. F of x equals 1/2 raised to the power of x. So we're going to do the exact same thing. We're going to create a table of coordinates for this function. And f of x is going to be 1/2 raised to the power of x. Now, if we substitute -2, -1, 0, 1, and 2 into this function, what are we going to get? 1/2 raised to the -2 power. What does the negative exponent do? It's going to create the reciprocal of this number, which is going to be 2/1, which is 2, raised to the +2 power. And that is going to become a 4. The next one, 1/2, if I raise it to the -1 power, we have to get the reciprocal of that, which is 2/1, which is 2, to the +1 power. And that gives us a 2. 1/2 raised to the 0 power. Remember that anything raised to the 0 power, it is automatically equals to 1. 1/2 raised to the first power, it is going to be 1/2, which is 0.5. And last but not least, 1/2 raised to the second power, 1/2 times 1/2, it is 1/4. And 1/4 is the same as 0.25. So basically these are my points: -2, 4, then -1, 2, then 0, 1, 1, 0.5, and 2, 0.25. So when we graph these points, let's put them in here. -2, 4, it is going to be up here. -1, 2. The next one is 0, 1. The next one is 1, 0.5. And the last one is 2, 0.25. So now on this one, we see a different story. As the graph goes to the right, the graph now it is decreasing. It is coming from the top, right? This is what basically we see. So it is decreasing, but as we increase the value of x, what is happening to the value of y? It is again decreasing to the number 0. So it keeps getting closer to 0. You see that it is getting a decimal, the decimal is getting smaller and smaller. So the fraction is getting smaller as we increase the value of x. So that means that this graph is going to keep approaching, approaching, and approaching, but it will never get to y equals to 0, which is my x-axis. Which again, we can say that this function has what we call a horizontal asymptote at y equals to 0. Now, the next thing that I'm going to show you is what are some of the properties that you need to know, once you see an exponential function. There are some properties that we can see they have in common if we compare the graphs, and those are these. These are the two graphs that I just showed you right now. First of all, let's go through the properties. Both of the graphs that we created, they have a domain of -infinity to +infinity because it keeps on going from left to right. So it never stops. both of the graphs start from anything above 0. So there was a horizontal asymptote at 0, meaning that they start from 0 to positive infinity, not including 0. That is going to be their range. Both of those graphs that we just graphed right here, both of them have this point in common, as you notice. They both pass through the point 0, 1. In other words, they have a y-intercept at 0, 1. Now, both of these graphs do not touch the x-axis, meaning that they both have a horizontal asymptote at y equals to 0, which is the same thing as the x-axis. So the x-axis, or the line y equals to 0, is my horizontal asymptote for those graphs. And the next thing is that, what about the graphs? One of them, we noticed that it was increasing to the right, the other one was decreasing to the right. How do we know if the function is increasing or decreasing? Just by looking at the base. If the base is bigger than 1, like you saw, the first example was a 5 to the x power, so the base was a 5. The function is going to be an increasing function, meaning that it's going to go up from left to right. Okay? Now, what happens if the base is less than 1? When I say less than 1, I mean between 0 and 1. So, which means a fraction. Like the example we just worked on, it was a 1/2 as a base. So, if the base is between 0 and 1, then the graph is a decreasing function, meaning that it goes down from left to right. And last but not least, these functions have what is called, they're both called, they are one-to-one, meaning that they have an inverse function. Because if I do a horizontal line test on each one of them, you see that the horizontal line intersects the graph, it doesn't matter where it's drawn, only once. So if I draw a horizontal line and it intersects the graph only once, that means that it is one-to-one, and one-to-one means that it has an inverse function. And I'm just going to give you just one thing about the inverse function. The inverse function has a name. We're going to cover that in section 4.2. It is called the logarithmic function. That's what it's called. Okay? So these are the general attributes of an exponential function. Now, let's start by looking at the transformations. This is basically the main thing of this section. We're going to start with this problem. Use transformations of the graph of f of x equals 2 raised to the power of x to graph the function h of x given below. Graph and give the equation of the asymptote, and use the graph to determine the domain and range of h of x. So we're going to begin by graphing the function f of x. And how do we graph it? By creating a table of values. Something that you already know about any function in the form b to the x power is that for sure they are going to start at 0, 1. They're going to intersect the y-axis at 0, 1. Also, we know that since the base right here is bigger than 1, this graph is an increasing function, so the graph is basically going to show us this, right? Now, to be more specific, I am going to get the points whatsoever, okay? We already know what the shape looks like just by looking at the attributes. However, I'm going to be more specific on what my points basically are. So, let's go ahead and replace the values of x as usual. -2, -1, 0, 1, and +2. So, if I substitute x with the -2, so 2 to the -2 power, remember the negative exponent represents the reciprocal, which is going to be a 1 over 2 raised to the +2 power, and that is 1 over 4. And 1 over 4 is the same as 0.25. The next one, 2 to the -1 power, that's the reciprocal would be 1 over 2 to the +1 power, which is 1/2, and that is 0.5. 2 to the 0 power, anything to the 0 power is equal to 1. 2 to the first power, it's going to be 2, and 2 to the second power, it's going to be 4. So for the function f of x equals 2 to the power of x, The points are -2, 0.25, -1, 0.5, 0, 1, 1, 2, and 2, 4. Right? So let's go ahead and create a sketch for this. So for my sketch, we see that, okay, we're going to have the point -2, 0.25, so which is somewhere over here. The next one is -1, 5, which is here in the middle, between 0 and 1. 0, 1, we already knew it was going to be there. 1, 2, and the last point is 2, 4. So to be more exact, this is exactly what the shape of this function is going to look like. And it keeps on going. Okay. Now what happens as the graph, as we decrease the value of x, the value of y, it is approaching 0. We already talked about that on the previous questions. So that means that this graph is going to keep getting closer and closer and closer and closer to the x-axis, but it will never touch the x-axis. Okay? So this is the graph of f of x, which again, we already know that this function has what we call a horizontal asymptote on the line y equals to 0. So let's go ahead and provide that information. That is something that we need to make sure we mention every time we do these functions. So for f of x, the domain of this function, it keeps on going from left all the way to the right. So we know that it's from negative to positive infinity. The range of this function, it doesn't get to 0, so it's anything above 0, right? So it's going to be from 0, not including 0, comma, all the way to positive infinity. And then we need to give the equation of the asymptote. Since this asymptote, it is going to be a horizontal asymptote, it has an equation of the form y equals, and the asymptote is y equals to 0. So these are three of the things that we're asked to provide. Okay. Now we're going to go ahead and do the function h of x. Now, how do we get from this function f of x to the function h of x? Well, there are two transformations that we need to apply. The first one, if you remember, we need to apply the +1 that is on the x. That +1 is going to make the graph go to the left 1 unit, meaning that it's going to be subtracted from the x values. We covered that in section 2.5. So if I subtract it from the x values, this is what my new function is going to look like. -3, 0.25, then -2, 0.5, then -1, 1, then 0, 2, and the last one is 1, 4. But that's not it. There's another transformation that we need to apply. So to finish my h of x, after doing the 2 to the x plus 1, then we also need the +6 on the side. What does that +6 have as an effect? It's going to shift the graph 6 units upward, meaning that all of the y values will be added 6. That was a change whenever we have a vertical shift. Okay. So then my new points are going to look like this. -3, 6.25, then -2, 6.5. Now look at the observation. What happens to the value of y now as we decrease the value of x? It is getting close to the number 6. Next one, -1, 7, then 0, 8, and the last one would be 1, 10. So then we're going to graph this one. So -3 and 6.25, it is going to be right here. The next one, -2 and 6.5, it is going to be here. -1 and 7, it is right here. 0 and 8, it is right here. And 1 and 10, it is right here. So the graph of this function is going to look like this. And it keeps on going up, right? And since you notice that we shifted the graph 6 units up, that means from previous lectures that we did that this horizontal asymptote also is going to be shifted 3, 4, 5, 6 units up. This is where the new asymptote for that function is going to be. So my new horizontal asymptote for h of x is going to be the line y equals to 6, meaning that this graph is going to keep approaching. It will keep getting closer and closer to 6, but it will never reach the number 6. That's my h of x. So what can we say about the domain of h of x? It is also from negative infinity to infinity because it keeps on going from left all the way to right. So all the values of x are in the graph. What about the range of this function? The lowest value is going to be anything greater than 6 because it's not going to get to the number 6. So it's going to be anything above the number 6. So it's going to be from positive 6 with the parentheses, which means not including 6, all the way to infinity. And last but not least, what is the asymptote of this function? Is y equals to 6. It gets close to 6, but it never reaches 6. And those are the attributes of the function h of x, and these are the attributes of the function f of x. Next function. Now we're going to discuss this one. Use transformations of the graph of f of x equals 4 raised to the power of x to graph the given function. Be sure to give the equation of the asymptote and the domain and range. Same thing. So, first thing that we must do again is that we need to start by graphing the function f of x. So f of x equals 4 raised to the power of x. So my points are going to be again negative 2, negative 1, 0, 1, and positive 2. So if I put 4 raised to the negative 2 power, remember that represents the reciprocal, which is 1 over 4 to the second, and that is 1/16. The next one, 4 raised to the negative 1 power, that represents the reciprocal, which is 1 over 4 to the first power, which is 1/4. Then anything raised to the 0 power by definition is equal to 1. 4 raised to the first power is 4, and 4 raised to the second power is going to be a 16. Right? Now, one thing is that 1 over 16 is going to be approximately 0.06. Okay? So it is approximately 0.06. This one is going to be 0.25. Okay? So for the function f of x equals 4 raised to the power of x, the points are negative 2, 0.06 approximately, negative 1, 0.25, then the next one is 0, 1, then 1, 4, and then 2, and 16. So let's graph the points for the function f of x. So negative 2. Now just keep in mind that the 0.06, it is very close to the number 0, right? So negative 2 and 0.06 is going to be almost touching the x-axis. Negative 1 and 0.25, it's a little higher than that. Then we have 0, 1, which is here. Then 1, 4, and the last one is 2/16, which we cannot see. So the graph is going to be again an increasing function, and once it goes to 1, then it's going to disappear after 1. And what happens to the value of y as we decrease the value of x? It keeps getting close to the number 0. Right? So that means that this graph is going to keep approaching 0, but it will never get to 0 as we go to the left side. Just keeps getting close to it. So we already know that this graph has what we call a horizontal asymptote on the line y equals to 0. Okay. So let's provide that information for the function f of x. So the domain, the range, and the asymptote. Based on this, we already know that the domain is anything from negative infinity to infinity because this graph goes to the left to negative infinity and goes to the right to positive infinity. All the values of x will be on the graph, negatives and positives. Now, the range it never gets to 0. So the graph includes all of the values of y above the number 0, which means that it starts from anything greater than 0 to infinity, not including 0. And the asymptote, it is located at the line y equals to 0. So this is for the function f of x. Now we're going to go to the function g of x. Now for the function g of x, like I was saying, is that we got only one little change that must be applied. So g of x is equal to 4 raised to the negative x. The only change is the negative on the x right here. Now, when we talked about this transformation as well, what is that negative going to cause on the function? Is going to reflect the function over the y-axis. So that's what that negative is going to do. And what effect is that negative going to have on the points right here? It is basically going to multiply. Negative x means basically the following. Multiply all of the x's times a negative 1. So all of the x's will be multiplied by a negative 1, which means that all of the x's are going to change the signs. That's what that negative in front of the x is going to do. So then my points are going to become positive 2, comma 0.06, positive 1, comma 0.25, 0, comma 1, that one stays the same, negative 1, comma 4, and the last one would be negative 2, comma 16. Let's graph those points. That's going to be g of x. So it would be 2, comma, and then 0.06. That one is almost touching the, we call the x-axis. 1, comma 0.25, so it's somewhere in here. Then 0, comma 1. Then negative 1, comma 4. And negative 2, comma 16, which we cannot see. So the graph now, you see what's happening. It is decreasing, right? Because it is, like I said, it is a reflection of this graph onto the y-axis, so it reflects to the other side. Okay, so now what happens is that we increase the value of x, the value of y, it is still approaching 0. So as we increase the value of x, so this is increasing the value of x, you see that the value of y, it is decreasing to the number 0. Okay, so this will be the function g of x. Now let's go ahead and write the domain, the range, and the asymptote of g of x also. Now for this function g of x, the domain, as you can see, it keeps on going to the left side and it keeps on going to the right side, which means that all of the values of x from negative infinity to positive infinity are on this graph. Now for the range, the lowest value of y, it is going to be 0, but it doesn't include 0. It's going to be anything above the number 0. That's where the points on this curve are going to be located. So from 0 to positive infinity, not including 0. And last but not least, the asymptote of this function is going to be the line still y equals to 0. So these are the attributes again for the function g of x. And this concludes this function. Now, the next one. We're going to have a couple of more that we need to graph. So I need to select just a few for this. So we are going to graph now this function right here. Use transformations of the graph of f of x equals e to the power of x to sketch the graph of h of x equals e to the power of x plus 3 plus 6. Alright, so let's begin by graphing f of x equals e raised to the power of x. Now we kind of talked about the number e before, back in section 1.4. I mentioned it to you, its value. So this is called a Euler number. So we're going to use again the same values to create the graph of it. So negative 2, negative 1, 0, 1, and 2. We already know that since e, remember back then the number e is about 2.718285 and so on. So its approximate value is 2.7. That means that since this base is greater than 1, and also it is an equation, it is a function in the form b to the x power, it's going to intersect the y-axis at 0, 1 again, and it is going to be increasing as it goes to the right. So this is basically what the shape of that function has to look like also. Okay. So, however, we're going to get a better estimate of the actual graph of e to the x with the correct values, with the correct points. Okay. So let's go ahead and do that. Next. So if I substitute a -2 into the x, that's e to the -2. For this one, that means is 1 over e squared. And then if you do that in the calculator, so you can do either 1 divided by e, you get the e by pressing second and ln key right here, and then I put the square. So 1 over e squared is 0.13, so it's about 0.1. That is its approximate value, 0.1. Then e to the -1, that's the same thing as 1 over e to the first power. And if I do 1 over e to the first power, 1 over and then ln, second ln, e to the first power, that gives me an answer of 0.36, which is about 0.4. That's its approximate value. Then e to the 0 power, anything raised to the 0 power is 1. E to the first power has an approximated value, so we're estimating, so I'm going to round off also. E to the first power is approximately equal to 2.7, and e to the second power, it is approximately equal to 7.4. Okay, these are the approximate values for that function f of x equals e raised to the power of x. So then the values will be -2, 0.1, -1, 0.4, then we got 0, 1, then we got 1, 2.7, and the last one is 2, 7.4. So we graph these points. -2, 0.1, it's going to be very close to the what we call the x-axis again. The next one is -1, 0.4. It is somewhere around this area. Then 0, 1 is already there. We knew that it was going to be there. 1 and 2.7, it is somewhere around this area right here. And 2 and 7.4. 7.4 is right around this area. So once we connect this point, this is what the graph of E more specifically is going to look like. And then it keeps on going up, right? As the value of x decreases, what do you see about the value of y? It is decreasing to 0 again. So that's something we already know about the horizontal asymptote at the line y equals to 0. So the graph is going to keep getting closer and closer and closer to 0, but it will never get to 0, right? So my horizontal asymptote for this function would be the line y equals to 0, right here in the middle. So we got the horizontal asymptote. So let's go ahead and give the information for the function f of x, which is the domain, the range, and our asymptote for this function. So we already know that the domain of this function is from -infinity to +infinity again. It keeps on going from left to right, meaning that all of the values of x, negatives and positives, will be on the graph. Now, for the range, it includes all the y values from above the number 0, because it doesn't get to 0, it's anything higher than 0. So it would be from 0, not including 0, to infinity. And the asymptote for this function, it is going to be the line y equals to 0. So these are the three attributes for the function f of x equals e to the power of x. Now, we are going to create the graph of g of x, h of x, which is e to the power of x plus 3 plus 6. Now, remember that the first transformation that must be applied, it would be the x plus 3. That plus 3 on the exponent is going to shift the graph 3 units to the left, meaning that it's going to be subtracted from all of the x values. That's what's going to happen to this 3. So if I subtract the 3 from the x values, then my new points are going to be -5, 0.1, then -4, 0.4, then -3, 1, then -2, 2.7, and the last one is -1, 7.4. But that's not all. There is one more thing that we need to apply. to finish the graph of h of x, besides the x plus 3, we also have a plus 6 on the side. Once again, what is the plus 6 going to do to the function? It's going to shift the graph 6 units up, meaning that all of the y's will be added 6 units. That's what's going to happen to this one again. All of the y values will be added 6 units. So we are going to do the points for this. Oh, but I should have done it on the new ones. It doesn't matter though, but let me put the plus 6s on the right side. I should have done it here. I don't know why I was doing the plus 6 to the previous one. Okay, so if I do the plus 6, then my new points, or my final points for the function h of x will be negative 5, 6.1, negative 4, 6.4, then we got negative 3, 7, then we got negative 2, 8.7, and then we got negative 1, 13.4. So let's go ahead and create the sketch of this. So my new points, and I want you to take a close look before we actually do it. Now the values of y are approaching 6. That's what's happening now. Okay, so negative 5, 6.1, it is somewhere over here. Then negative 4, 6.4, it is around this area. Then negative 3, 7, it is right here. Then negative 2, 8.7, it is somewhere over here. And the last one we cannot see it, which is negative 1, 13.4. So it would basically be somewhere up here. This is what the graph of this function h of x is going to look like. Okay, and now as the graph goes to the left side, you see that once I shifted the graph 6 units up, this horizontal asymptote was also shifted 6 units up. So now it is going to be at the y equals 6. So the graph now is going to keep getting closer and closer to the number 6, but it will never get to 6 right here. So that's what's going to happen. As the value of x decreases, the value of y keeps getting closer to 6. So let's write the last pieces of information for this problem. It is the domain of h of x, the range of h of x, and also the asymptote of h of x. So the domain of this function is also from negative infinity to positive infinity, because it keeps on going from left to right. The range is from 6 to positive infinity, because the lowest y value, it is 6, but it never gets to 6, so it's anything above 6. And the asymptote would be the line y equals to 6. And that concludes this problem as well. Next question. Now we're going to do this transformation. So we're going to use transformations of the graph of e raised to the power of x to create the graph g of x equals 2e raised to the power of x. This will be the last one that we're going to analyze here. So basically, we're going to do the same thing. Negative 2, negative 1, 0, 1, and 2. So when x is equal to negative 2, so e to the negative 2 power is the same thing as 1 over e squared. And we just found that value. It was 0.1. E to the negative 1 power, that's the same thing as 1 over e to the first power. And we also found that value, which is 0.4. E to the 0 power, anything to the 0 power is 1. E to the first power is equal to 2.7. And e to the second power is approximately equal to 7.4. So we got the approximations for these values. Okay. So my function f of x equals e raised to the power of x contains the points negative 2, 0.1, negative 1, 0.4. 0, 1, 1, 2.7, and 2, 7.4. So we're going to graph those points in here to create the sketch of the function f of x. Alright, so my points for this would be -2, 0.1, which is almost touching the x-axis right here. Then -1, 0.4, somewhere around this area. 0, 1, we knew that that one was going to be there by definition. 1, 2.7, which is somewhere around this area. And the last one is 2, 7.4, which is somewhere around this area. So that is going to create my function f of x. And as the graph goes to the left side, it keeps approaching y equals to 0. It never gets to 0, it just keeps getting closer and closer to the value of 0. So once again, my horizontal asymptote is at y equals to 0. So we're going to say that information, the domain is from -infinity to +infinity as well. The range is still from 0 to infinity, and the asymptote of this function, it is going to be the line y equals to 0. This is the information for f of x, which is this. Now, let's create the graph of g of x. Now, for the function g of x, there is only one little change. What do you see as a change here? There's a 2 in front of the function. That number is being multiplied. That, remember, when we multiply a constant to the function, that is going to create a vertical stretch or vertical shrink depending on the value. If it is greater than 1, like this one, it is going to create a vertical stretch. That's what this one is going to do, a vertical stretch. And how do we get the vertical stretch? We multiply all the y values by that number. Whether it is a vertical stretch or shrink, we always multiply the y values by whatever number is being multiplied in the front of the function. So it's going to give us -2, 0.2, then -1, 0.8, then 0, 2, then 1, then this one is going to be a 5.4, and then this one is going to be 2, and it's going to be 14.8. So when we graph them, -2, 0.2, it is going to be a little bit higher somewhere over here. The next one, -1, 0.8, it is somewhere over here. Then 0, 2, it is here. 1, 5.4, it is around this area. And the last one is 2 and 14, that one is way up, we don't see it. So this is what the vertical stretch basically looks like in this problem. And as the graph keeps on going to the left, it keeps approaching and approaching still. As you can see, y equals to 0. That's what the values of y are getting close to. So right here, the asymptote of g of x doesn't really change. So basically the domain, the range, and the asymptote are all still the same thing. Domain is still from -infinity to infinity. The range is still from 0 up, which is from 0 to infinity. And the asymptote of this function is still the line y equals to 0. And that concludes this problem. Now, what we are going to do next is we are going to cover the formulas for compound interest. This is telling me the following, that after t years, this is an application of exponential functions. After t years, the balance A in an account with principal P and annual interest R in decimal form is given by the following formulas. Now, if the interest is compounded a specific number of times during the year, then we're going to be using the first formula. What does it mean by the interest is being compounded a specific number of times during the year? It will basically add up interest based to the balance that many times during the whole year. So if I say that we have an interest that is compounded quarterly, that means that the interest is being compounded every third month, meaning it's going to be compounded 4 times during the whole year. So we're going to look at the different number of compoundings. So n compoundings. And these are the different types of compoundings for the value of n. So if I say that the interest is compounded annually or yearly, that means that n is equal to 1, which is gonna calculate the interest 1 time during the whole year. Now, if the interest is compounded semi-annually, that means every 6 months. So it's gonna calculate the interest 2 times during the whole year. Now, if the interest is compounded quarterly, that means that it's going to be calculating interest every third month. So it's gonna be 4 times during the whole year. If the interest is compounded monthly, that's the next one, I forgot that one, then that means that it's going to calculate interest for every month, meaning for 12 months during the whole year. So that would be n equals to 12. If the interest is compounded weekly, then we can say that n is equal to 52 times during the whole year. If the interest is compounded daily, then we were going to say n is equal to 365 days in the year, and so forth. Okay. Now, on another note, if the interest is compounded continuously basically means that the interest is being generated or calculated like all the time from the moment that it was invested. So that one, there is no value of n. So for that, we use a different formula. This is the specific formula that we're going to use when the interest is being compounded continuously. So, once again, this formula is going to calculate how much money I'm going to have in my account A if I invest P dollars in that account at that interest rate. This many for an interest rate being compounded this many times during the whole year for this many T years. Okay, that's what that formula tells us. Now we're going to answer the following questions with this compound interest formula. We're going to use the compound interest formula, A equals to P times 1 plus R divided by N raised to the NT, and A equals to P times E raised to the R times T to solve the given problem. Round the answers to the nearest cent. Now the question is, we want to find out what is the accumulated value. So basically it's asking you to find the value of A. That's what the accumulated value, basically how much money I'm going to have in my account. If I invest $10,000, that is my P. The P represents the principal balance, which is my initial investment. For 7 years, that's the time. So it's going to be invested for T equals 7 years. At an interest rate of 4%, but the interest rate must be given in decimal form. So to make that 4% in decimal form, all we have to do is divide it by 100%. And if I divide it by 100%, it's the same thing as moving the decimal 2 times to the left. So that becomes a 0.04. Now, we're going to first work on letter A. It tells me that the interest is compounded semi-annually, meaning that the interest is compounded 2 times during the whole year. So that means in this case that n is equal to 2. So we're going to go to the formula for compound interest, which is A equals to P parentheses 1 plus R divided by N raised to the N times T. And we're looking for A when P is equal to $10,000, which is my investment, when the rate is 0.04, which is 4%, and it is invested for 2 times during the whole year. So and 2 times during the whole year for 7 years. Okay, so we're going to use the calculator to find the result for this problem. So we're going to do $10,000 parentheses 1 plus the rate, which is 0.04, divided by n, which is 2, everything raised to the power of 2 times 7, and we close a parenthesis, and that gives us the amount. So that means that if I invest $10,000 at an interest rate of 4% compounded semi-annually for 7 years, At the end of the 7 years, I'm going to accumulate $13,194 with 79 cents. So that's going to be $13,194 with 79 cents. This is how much money I'm going to have after the 7 years if the interest is compounded semi-annually. Letter B. For letter B, it's basically going to be the same deal. Now the only difference is that the interest now is going to be compounded quarterly. Basically calculating the interest every third month, 4 times during the whole year, meaning that n is equal to 4. So the formula, A equals, my investment is $10,000 times 1 plus the rate is 0.04, which is 4%, divided by 4 because it's 4 times during the whole year, raised to the n, which is 4 times the time, which is set for 7 years. So we're going to calculate how much money I'm going to accumulate if I invest $10,000 at an interest rate of 4%, with the interest being compounded quarterly for 7 years. At the end of the 7 years, we're going to have, and we just have to make the calculation. So it's $10,000, parentheses, 1 plus r, which is 0.04, divided by n, which is 4, raised to the n, which is 4 times t, which is 7, close the parentheses for the exponent. And that means that after the 7 years, I'm going to accumulate $13,212 with 91 cents. This is how much I'm going to accumulate after the 7 years if the interest is compounded quarterly. And you see, of course, calculating the interest more times with the same interest rate, of course, is going to lead or yield to a higher amount in return. Okay. Next, letter C. For letter C, it says that the interest is compounded monthly. Monthly means that it's going to generate interest every month. So n is going to be 12, meaning that it's going to generate interest for 12 times during the whole year. So A equals P, which is $10,000 again, times 1 plus R, which is 4%, 0.04, divided by n, but now it's 12 times during the whole year, raised to the n, which is 12 times 7 years. And we're going to find out how much money I'm going to have after investing this money, $10,000 at an interest rate of 4%, compounded monthly for 7 years. At the end of the 7 years, we're going to have this much. So let's calculate it. $10,000, parentheses, 1 plus the rate, which is 0.04, divided by 12, close parentheses, everything raised to the open parentheses, 12 times t, which is 7, close parentheses, and that gives me $13,225 with 14 cents. So this is how much I'm going to accumulate after the 7 years, if the interest is compounded monthly. Last but not least, I'm going to find out how much am I going to accumulate if the interest now is going to be compounded continuously. This means that it is constantly adding interest all the time. So we're going to use a different formula for this. A equals to the PERT formula, P times E raised to the R times T. That's the formula for continuous compounding. Now, the principal balance, which is P, is $10,000. E, we already know what it is, so it's just a number. The interest rate is 0.04 times the time, which is 7. And that is going to give us how much money I'm going to accumulate if I invest $10,000 into an account paying 4% compounded continuously for the after the 7 years. This is how much money we're going to have. $10,000 times E, second ln, raised to the 0.04 times 7, and close the parentheses. And we're going to accumulate $13,231 with 30 cents. $13,231 with 13 cents. And this is basically all what needs to be taught from section 4.1, which is exponential functions and their graphs.